Well, thank you for that introduction, and thank you for having me. It's always fun when you get invited to come speak to a new group of people that have a different background and different, think about similar problems, but think about them differently than I have for quite a while. And I was especially interested in that the structure of the afternoon is hopefully a short lecture. I have a small problem once I start talking. I keep talking, but I'll try to do my job. But then followed by an extensive question and answer period. And I think there is a schedule, but since my flight is not until around 1 o'clock tomorrow, I've got plenty of time, and I'll answer whatever questions anybody wants to ask. So I'm going to talk about the end of oil, and the starting talk was just that, thinking about the end of oil. And then as I started putting this together, in the conversations with Elaine and the staff here, it occurred to me that I'd better put the subtitle in, and that is that, well, maybe it won't run out. And we want to think about this maybe a little more broadly and differently as we go forward. Now, there are a lot of aspects to the end of oil. Does it run out? Does it not run out? And first and foremost is there's just a lot of it out there. This was my job for 30-some years, is finding new supplies of oil and gas around the world. And this is a little map, and I bring some props with me just so I keep. So here's what we're talking about. This is something like 1 billionth of the world's known supplies of crude oil. So it's a little rather precious. We'll keep it right there so we just remember talking about. And then, of course, I have my own little version of the map, because I like to keep it close to remember where it is that this stuff is located. And by the way, there's a similar version for gas. So we can look at oil, we can look at gas. What we see is it's distributed around the world rather broadly, but certainly not uniformly. And that is a bit of an issue when we get down to thinking about developing it and moving it, and certainly the politics involved. But on the oil side, there is a lot of it. This is something like, this is the discovered reserves plus where geologists like myself think there's a lot of undiscovered resource. And this is on the order of 2 trillion barrels of crude oil, 1 trillion barrels being 42 gallons. So it's a lot of oil, 2 trillion barrels. This is something like, well, just reserves alone, 40 or 50 years supply. If we add the undiscovered volume to it, at today's rate of production, we're talking 50 or 60 or more years of supply of crude oil. So it's not like it's ready to run out tomorrow. And gas is a similar, maybe even more plentiful resource. These dots represent something like 6,000 trillion cubic feet of natural gas. That's just the known established reserves. There's another few thousand trillion cubic feet in similar geography that has yet to be discovered. Again, we're looking at least 60 years supply at today's rate of production. So that's the starting point for this. There's a lot of oil and gas out there. So if you think that it's going away anytime soon, it's not going away soon because of the number of molecules available. That's not what will change the world. That's one of my key points. Now, when we step back broadly and look at the energy system as a whole, this is what it looks like. This is a picture from Shell. The data is based on 2007. I don't think it's that much different than today. Oil represents about 1/3 of the primary energy consumed in the world. Natural gas, a little over 1/5. Coal is significant globally. It's about 1/4 of world energy supplies. Biomass is around 10%. Now, that biomass is not fancy bioengineered renewable stuff. That's people going out and picking up sticks and wood and dung and whatever else they can find that would qualify as biomass and using it for heating and cooking. All right, so that's pretty low-tech biomass. Nuclear, 6%, renewables, about 4%. That's the picture. And that's the supply, and the demand is down at the bottom. A little over 1/4 goes into mobility, about 1/2 into agriculture and industry and services, and a little over 1/4 in residential use. So that's the picture as it is today. But this is not a static picture. And here's one of the first key points. It's really not a static picture. And I will talk about peak oil in one sense, if any of you have followed that concept of peak oil, that we're producing so much that inevitably, well, it's a finite resource, but inevitably it will decline. But there's another kind of important peak oil that I think is worth mentioning, and that is from the supply perspective. Right? Oil today is 34% of our primary energy supply. There was a peak oil in 1980 or so, 1980 to 85, where oil represented about 50% of primary energy. So we passed that peak, and the share that oil has been providing to primary energy has been declining since. Now, we've been using more and more. I'm not pretending not, okay? But its significance in terms of dominating the energy flow has been declining for 30 years now. And nobody actually even noticed this peak. It's come, it's gone, it's passed. And that tells you something about the dynamism of the energy markets. The other things have come in to fill the gap. So we passed one peak oil 25 or 30 years ago. And by the way, that's not so crazy and so weird, because in 1920 or so, we had peak coal, where coal was about 70% of global energy supplies. And maybe 100 years before that, we had peak wood, where, before the advent of coal and then petroleum, wood and conventional biomass accounted for nearly essentially 100% of global energy supplies. So that brings us, sort of grounds us in how this energy market has changed and how we've gotten to where we are today. And then there's a question of, well, where are we going? Right? What's the future look like? And that's really what I want to talk about. Well, there are two things about the future I'll say right up front. One is on the demand side. Electricity today accounts for something like 40% of primary energy consumption. Primary energy, about 40% of primary energy is consumed to generate electricity, which then goes into the marketplace to be used. That's a significant increase. Just 3 or 4 decades ago, that was about 20%. So there's one new peak that's coming from the demand side: electricity. Much more in demand than ever in terms of its share of the global energy supply and how it feeds into the marketplace. And also, probably because of the sheer number of molecules that are out there and the usefulness of them, I think what we're also seeing as we look into the future a few decades away is peak gas, where natural gas, its share of the global energy supply is grown significantly over the last few decades. That will continue to grow. And maybe in 2 or 3 decades from now, we see that natural gas accounts for something like 50% of global primary energy supply. Where it goes from there, I don't know. Does it continue to increase? Is there truly a peak in that point and then decline? I'm not into making predictions, but there will be a peak gas. And in this context, it will then decline. And out ahead of 2040, we get to 2050 and on to the turn of the next century, we're looking at probably peak renewables, where in fact new ideas and new renewable energies will constitute the bulk of our primary energy supply. And we'll then now talk some more about that. But when we want to talk about the future, we have to think about it I want to think about it in some sort of concrete ways. And I'll boil it down to a few choices. There are choices in how we can think about the future of energy. What do we want to consider in terms of the future energy? The first choice, and by the way, I put these up here not being, I'm not criticizing any of these choices. They're actually all valid. Some of them are actually the way certain players in the system, whether they be companies or politicians, whoever's actually think about it. But choice one is we actually just bury our head in the sand and we don't worry about it. And maybe there's some logic to this, because here's a picture of energy supply and demand from the 1970 on, and what we see is energy demand has grown significantly around the world. Energy supplies have grown significantly and to some extent diversified in the sense that, again, back in 1980, oil dominated. That's no longer the case. It's now a more broader supply. And we go off into the future, and we have coal gas. This is coal that's being gasified with the idea that starting a few decades from now, the carbon dioxide that's created from that gasification process can then be sequestered, so that coal gas is actually now a reasonably clean resource. Oil is still a major source. Natural gas is approaching its peak in terms of its share of primary energy market. Then there's nuclear and hydro, which both grow a little bit. And then up on the top, we have bio and renewables and others fitting in. So what we see going forward, and this is a picture that comes from Shell's energy scenarios to 2050, is continued development of energy supplies and energy markets around the world. And so, okay, maybe the logic of I just don't worry about it is because, look, we've gotten through this for hundreds of years. There's plenty of molecules out there. There's plenty of capacity out there. There's plenty of smart people out there. We'll get through the next several decades, and things will just kind of rattle on as normal. There are actually a lot of people that think about this, and sometimes I imagine that must be what they think in the United States government, because why else would they not have developed a rational energy supply from the early 1970s when the Department of Energy was first created? I don't know. No value judgment there, just observations. Now, I'll tell you something about this picture, which I sort of glossed over very quickly, but it's rather important as I kind of look at what other sort of options and choices there are about the future. Bio-other is actually code. Now, see, I come from inside this company, so I know these things. It's code for, well, we don't know quite what it's going to be. But if we're going to meet that demand that we imagine happening, primarily because of growth in Asia and other developing countries around the world, it's going to have to be something. So we'll call it bio-other, and we'll figure out as we get closer to mid-century what bio-other actually is. Now, we'll talk some about that, and we'll see what some of the options are. But that sort of frames out our first sort of choice about what the future of energy might look like. Now, there's another choice. The second choice is a little more thoughtful because I'm actually going to use some data. But choice two is, this is actually pretty straightforward. It's a big system. It's a fairly stable, although complex system, but I can actually make some reasonable predictions about the future just by extrapolating from the present. And if I go back to the slide, that's to some extent what's going on here. I could use this picture to say that that's a reasonable approach. I'll just extrapolate from the present. I'll sort of put an overprint on there of where I know the molecules are and some of the complexities, but in fact, I can get to the future simply by making these extrapolations. Now, when I do that, something else happens, which is really rather comforting, because I haven't talked yet about climate, a growing concern in some people's minds, a growing problem in many other people's minds. But if I take the last few hundred years of history and extrapolate into the future, I have a very comforting story about climate. And that is this. On the vertical scale here is the hydrogen to carbon ratio. So it's a proxy for how much carbon is in the energy we use. On the horizontal scale, if you can't read the numbers, it's 1800. The year 1800 is on the left. The year 2100 is over here on the right. And the blue dots are real history. Right? So what we see for a few hundred years of real history is we've been systematically decarbonizing our energy system. So now if I like this option of how to think about the future, well, I can do a lot just by taking the past and extrapolating. I can give myself a lot of comfort in terms of what the future energy supplies and the state of the globe might be, because, well, I can imagine, at least, or maybe even some would predict, I wouldn't, but some might, that we'll continue to decarbonize our energy system and we'll continue out this line, and this is a good thing, taking carbon out. And it's actually, there's some logic to this. I mean, this stuff is much more energy dense than wood. It's more energy dense than coal. There's a reason we've moved along this path, because it's not only taking carbon out, it's making the fuel source is much more energy dense. It's much more efficient to move around the globe to satisfy energy demand with. Methane, again, more energy dense in terms of I'm not moving nearly so much carbon around. And hydrogen is much more energy dense in terms of chemical energy than is methane or crude oil or coal or wood. So there's some logic to moving along a path like this. But I would say it's dangerous to just imagine that it happens on autopilot. Now, there's something else about extrapolating. If you're going to take this approach that I can predict the future by extrapolating from the present, I can't just take the good news. I have to consider the challenges in that as well. And one of the important challenges is this, and that's infrastructure matters a lot. In a global business such as energy, where I'm moving huge volumes of fuels around, feeding economies in really, really enormous volumes of fuel, infrastructure matters. And what's important is infrastructure takes a long time to build out. Any national or global scale infrastructure takes decades. And here are examples. And this is, again, I'm looking at the past and asking what could happen in the future if I do actually change over. If I change over from running automobiles on a derivative of this, and I'm going to use natural gas, or I'm going to use some hydrogen fuel source. Well, I get the hydrogen somewhere. But if I do something like that, then what am I going to do? Well, I'm going to have to build out new infrastructure. I'm going to have to build pipelines. I'm going to have to build new service stations. I'm going to have to do something to bring that fuel to people, and that's going to take time. And any time in the last few hundred years when we've built out national and global scale infrastructure, it hasn't happened quickly. It takes on the order of a century, right? And that could be canals, railroads, telegraphs. It can be the road systems that we have. It can be the airline system. It can even be the internet. I mean, the internet's been around for 30-some years in fledgling ways, but it's now, okay, it's past 50% penetration in households in the United States, a little more than 50% penetration in businesses in the US. So it's getting there, but still, it's taken decades to get there. So global scale infrastructures take a lot of time. So this is important. If I'm thinking about getting to the future by building on the present, I have to think about the infrastructure side of this and what happens. So now, there's some other options I want to consider, but I also want to take a step back and think about energy in some different ways to frame the problem differently. And there are really three very simple energy imperatives that we have to think about. And today it's important, tomorrow it's always been important. The acceptability of energy sources in terms of cleanliness, it's key. The availability and the accessibility. All three of these are rather important in terms of framing the future of supplies of energy. Now these actually, I think I stole this slide from Shell. I guess I didn't steal it since I worked for them for so long, but I kept it with me when I left. But I like to, and these words are okay, and if I'm a high-priced consultant, I'll use long words, but it actually comes down to very simple short words. And that is that the even simpler imperatives are people want energy that's clean, cheap, and convenient. And this now frames quite a lot about thinking about energy and thinking about the future of energy and where we go. And let's not forget that in clean, cheap, and convenient, there are a lot of things working in this energy system that are going to impact that. I've got markets up and down the energy value chain. I've got social and political systems that are going to be operating on this. And this picture is drawn in a rather interesting way, not by accident. Clean, cheap, and convenient being drawn as points in a triangle, sort of like they don't all go together because sort of like they don't all go together. Right? It is what Shell calls a trilemma. And in fact, what you find is clean, cheap, and convenient are often working against each other. And what you'll also find when you look at it in some detail is the markets and the politics and the social systems and the suppliers and the consumers are not even all over in the same places. They're also in many ways working against each other in feeding this energy system. And that becomes critically important in thinking about the future of energy and how it happens. And we look at that, let's just think. First, go back to my energy supply-demand chart that I showed, and potentially by the year 2050, energy demand doubles from what it is today. Now, a lot of assumptions in there in that scenario around the marketplace and around developments in Asia. Okay, maybe it's only a 50% increase. It's still huge. Okay? Significant growth in energy demand between now and mid-century and continued growth beyond that. And okay, energy demand, that's us, that's consumers. What do we want? Well, mostly we want cheap. And second, mostly we want convenient. And more, we're starting to think about clean because over the last few decades, we've come to realize that that matters. But in fact, cheap and convenient counts for as much as anything. At least in the United States, when they do market research on where to site a petrol station, forecourt, the dominant factor that goes into this is the knowledge amongst the business of retail and gasoline that people will not turn left. Sorry, I'm in the United States, so bear with me. People will not turn left to go buy gasoline. So in this country, people would not turn right to go buy gasoline. So you put the service station on the corner where it is most convenient. And then if you've got two corners there that are equally convenient, price starts to matter. And then all the marketing that's done in the background about our fuel is cleaner than their fuel, it probably is very much in the background. And this is the real world of consumers. Right? And it's something we have to think about in terms of the future of energy. So where in this picture are the consumers and what are they asking for? Now, we also have the energy supply. And in any scenario that's put together, I would say rationally, looking at supplies, looking at the systems, the infrastructure, and everything else, hydrocarbons are going to be a foundation of the energy supply system for decades to come. And when we look at that, okay, well, here's that current energy supply, and look where they are on the sides of this triangle. Somewhere between cheap and clean, you've got natural gas, wind, and solar, increasingly more expensive as you go down towards solar, but getting cleaner. That's a good thing. Over on the cheap and convenient side, well, the cheapest of all, really, it's coal, and oil's right there. Nuclear is pretty cheap and a little less convenient, but still pretty good. But over here on the coal, oil, and nuclear side, these aren't necessarily clean by lots of people's measures. Somewhere in the middle, and I didn't know quite where to put it, is a sort of fledgling first-generation bio stuff. So I put a question mark, and then I hedged a little more and put an arrow with another question mark, saying I'm not quite sure where it is. It clearly doesn't occupy a sweet spot yet, because there's a lot of debate about today's bio, which is dominated by ethanol mixed into the motor fuel stream, that bio is not actually much cleaner than conventional oil. Some would say it's a slightly dirtier, some would say slightly cleaner, but it's kind of on par with conventional oil. It certainly isn't any cheaper. It survives and has grown to where it is by legislative mandate and by really fairly generous tax credits and economic incentives. But okay, but it's there. It's on the picture. But that's where it is. Now, this doesn't look anything like the picture we had a minute ago for where the consumers were. Right? It's very different. But I can't change these things. I could change consumer behavior, and we've seen that over the last several decades as people have become a little more interested in clean, and some people will actually spend money to be cleaner. It's why the Prius, Toyota Prius, has made its way into the marketplace, because there are some that say, look, it's just worth it to me. I'll pay a little bit more. And many studies show that on a per mile basis, it's a more expensive mode of transportation than a conventional gasoline-powered automobile of the same size and shape. But some people say it's worth it to me because I'm so we can change consumer behavior, but I can't change where coal and oil and natural gas and nuclear are on this kind of a picture. Now, I can work on it a little bit, but I can't change the fundamentals of it. So now this takes us to a third choice. And the third choice is, well, it's actually thoughtful in its own way. This is a very difficult picture I've just built. I mean, I've just got this problem. And I've got this growing demand, and oh my gosh, what am I going to do? By the way, I haven't talked about politics yet. I'll get to that. But this is just a big, messy, challenging problem. So the third choice is, well, I'm just going to hope that a miracle occurs. Now, from the point of view of the whales, in about 1870, I suppose petroleum did look like a miracle. But I think that's actually asking quite a lot. This is what happens going forward. But unfortunately, there are some people I listen to them on U.S. talk radio. I see them in government. I even hear them in business. And by golly, I imagine, and this is this doesn't, it sounds like a criticism. It doesn't, I don't mean to be criticizing them for their motives or beliefs, but this is, I think, their choice. This is what they imagine about the future of energy, that, well, it's happened in the past, you know. We managed to as the earth was becoming deforested, we discovered there was this magical coal stuff of ancient forests, and as the air was getting really filthy dirty, we found this, and we're running out of whales, we found this petroleum stuff, and now there's natural gas, and gee, that for decades that was just an uncomfortable byproduct from the oil industry, and you know, with markets only in a few places around the world, so yeah, why not? There are a lot of smart people working on this with a lot of interesting technology, and sure. And you know, there are lots of people, I imagine, they say, well, I don't know what better to do about it, so I'll just imagine that somewhere out there a miracle will occur. And problem is, I haven't talked about the last little part of this, and that's, which makes miracles even harder, by the way, is this whole policy, regulatory, legislative side of thing. And this is, again, another reality. And when I put energy regulation on this little triangle of clean, cheap, and convenient, they're again in very different places than the consumers and in very different places than the producers. You know, when I was talking about energy supply, I actually left something out. I talked about the consumers who want it cheap. I forgot to mention the resource holders that don't necessarily want it cheap. So even when you're just in one segment, talk about supply, there's this tension between on just one aspect of the triangle, cheap. Now when I get the regulators and legislators involved, it gets even more complicated. So we take our gas, oil, and coal, and there's a lot of talk about carbon constraints, and carbon sequestration has the potential to take gas, coal, and oil and move them down towards that clean corner of the triangle, but at a cost, certainly at a cost, and certainly not making, as fuels, not making them any more convenient. Any reasonable estimates done about carbon sequestration, if it's going to be a viable way of managing carbon dioxide emissions into the future, the scale of, back to infrastructure, the scale of the transportation, the pipeline system that's going to be necessary to move the carbon dioxide from the power plants to the sequestration sites is on the same scale as the current systems that move oil and natural gas around the world. So we're not making things any more convenient by going to carbon sequestration. We can help ourselves on the clean side. It's going to be more costly. That's the reality of it. And that's just one aspect of regulation. There's taxation. And this gets even messier when some of these taxes are often they're imposed by the resource holders. So now I've got the taxing authority who pretends not to be on the supply side, but in fact is, because in many countries, in most countries, the taxing authority is the landlord, is the regulator, serves many roles. But taxation fills into this, and energy companies, and I can be pretty sure this will be true for the first very, very profitable, very successful renewable energy companies. They will be very attractive targets for the taxing authorities, and that's just another reality of it. And then you've got politics, and this can be global politics in terms of where the oil is and how it's got to get to where the consumers are, or it can be very local politics, such as shale gas development in the northeast of the United States and people in rural eastern Pennsylvania not necessarily wanting to see 100,000 gas wells drilled in their backyards, and even France, where fracking is being regulated heavily or even outlawed as a way to stimulate natural gas production. So all of these things come in from the regulation side, have a huge impact on the supply-demand picture, and certainly have some impact on the future of energy. And just as another kind of frame this out a little bit, just take oil and natural gas as proxies for most of the energy system. There's actually easy stuff and hard stuff when you're considering how do I continue to develop this resource. And I could look at oil and natural gas. I could do the same picture for solar, for wind, for nuclear, for any other. I choose oil and natural gas because it's what I know well and I can feel comfortable talking about. But where the oil is, finding it out there, that's actually pretty easy. Petroleum geology is a pretty well advanced science. We know where this stuff is, how to go find it, how to move it out of the ground. What's actually more difficult is predicting what's going on or what could go on thousands of feet below our feet, and then managing the politics of that not so uniform distribution of resource around the globe. So there's easy stuff, there's harder stuff. There's economics is usually pretty straightforward. And I'll tell you a little secret from an oil company insider. There's nothing more profitable than a producing oil field. Nothing in the world is more profitable than a producing oil field. That's why the taxing authorities love oil companies so much, even though they say they don't. They actually do, because they make a lot of money. What makes it hard, though, is the commercial agreements around structuring the development of a major field and moving that product into the marketplace. And that could be just straightforward commercial agreements between equal players on different parts of the supply chain, but quite often it also involves countries and governments, which make these commercial agreements even more complex. And then easy stuff is that this is a well-established industry, 100+ years old, very mature technologies, a lot of skill and know-how in doing this, operating at an enormous scale around the globe. I'll talk about that in a few minutes. But that actually rolls into some harder stuff around oil and gas policy. It turns out that in many political circles, at least some that I'm familiar with, that established industry, that expertise, and that capability is seen as suspect. And if not suspect, it's certainly seen as something that needs to be imported into a different country, moved in a different way, or managed in some fashion. So oil and gas policy starts to become a very important player in this business of managing this future resource around this established industry. And then finally, back to this climate thing. There's this business of carbon intensity, which is actually pretty straightforward. All right, I know how much carbon there is in here. I know the energy content of this. Give me a fuel, I can do that. It's chemistry, it's pretty straightforward. But now, fuel substitution, what do I do instead, starts to become messy and difficult and challenging. So again, there's easier stuff and there's hard stuff. So before I move on to another choice, I want to actually expand on one of the things here, and that's the business of politics. And just to add one more dimension to this thing, this is global business. There's you can find it, Price Waterhouse does this every few years, where they look at countries around the globe, and for each country they come up with what they call the Opacity Index. Opacity in this context generally being not such a good thing. They look at legal and social and tax and financial systems, judicial systems in these countries, country by country, and they basically grade them on how transparent or opaque they are. And in this case, they give each other a score, which they call the Opacity Index, and in most business worlds, opaque would not be necessarily a good thing, so a high score is really not what you want. Now, what I did was I found this score for these countries from Price Waterhouse, and then I cross-plotted it on the vertical scale with the estimated resource volume, where the oil and gas is around the world, based on many people's estimations, the USGS and companies like Shell. And this is what it looks like. And what it looks like is, well, let's see, over here on the far left, down in the corner, with an opacity index of around 17 or something, is Finland. And I guess what this means is if all the oil and gas in the world were located in Finland with their systems, judicial and tax and legal and financial systems, we wouldn't worry so much about it, would we? The problem is most of the oil and gas is not in Finland. It's located in a bunch of countries out here in the middle of the chart with opacity indices of 40 or 50 or more. And that is the root of a whole nother problem, is the oil companies are going to have to operate in places where it's just not so clear what operating means. And because the oil is then moved around the globe, the people in the consuming nations are going to have to deal with the consequences of that as well. That's just a reality of this business. So now this brings us back to this picture. And because what I mentioned at the beginning, but there's the distribution for the primary energy demand going forward, looking sensibly ahead to mid-century. And if you looked at that and you looked at where the dots are, you'd find some overlap, but not complete overlap. So we're into this little problem of political problem of the supply is not necessarily where the demand is. So now we come back to our fourth choice, and where I want to now really think about what the future looks like. And the fourth choice is really a world of innovation and adaptation. It's not particularly easy, but it is the way that we actually go back to this picture and turn bio-other into something real and realizable and doable on a global scale. And innovation and adaptation is the answer, and it's the only sensible answer. And it's innovation and adaptation on the technical side with science and technology. It's on the business side in terms of companies and their economic and commercial models, and it's on the government side in terms of tax and policy decisions. And that is the only way we go forward. And I could end here. I could, but I won't. Because I want to fast forward and actually think, okay, I'll be the technologist guy here, and I'll think, well, what could this actually look like on the technical side? And what could I actually say about looking forward 100 years? What would the system of energy actually look like if this actually came true, if this was our choice, that on the technology side we were to innovate and adapt? And I'm assuming in all of this that the social and the financial and legal systems allow this kind of technical innovation to occur. So I want to do that. And I'm going to do that, I'll start here. Start here with, by going back in time to the periodic table. Now, the wonderful thing about lecturing in a place like MIT is you don't have to spend a lot of time explaining. But I'm assuming everybody's familiar, at least, with the notion of the periodic table. So this is the periodic table. And because I have my little props, I got one right here. Keep it close. Now, the remarkable thing about the periodic table is this. For hundreds of years, this is how we built it up, as this beautiful two-dimensional picture, and each box has a lot of numbers in it. And these are all constants, every element. And it's just a subset of them, because all of these elements have a whole lot of other constants. They've got magnetic susceptibilities, and if they're a gas, they diffract wavelengths of energy in certain ways. All kinds of different things are constants about each one of these elements in each box on this periodic table. And we know that. We've known that for decades. Until the world of nanotechnology comes along. Now, here's a picture taken from an experiment at MIT. And what's really interesting about this picture is that it blows this notion out of the water that all of these are constants. Because what this is, in each of these 6 vials, there is the same gas, the same substance, the same element. What's different in each of these is that in one, it's nanoparticles of a few tens of atoms, and in the middle it's a few hundreds of atoms, and on the right it's a few thousands of atoms. That's all. Right? But it's the same stuff. But when I shine light on it of a fixed energy, it radiates light out at different wavelengths. Right? So I shine consistent light on the same material, and it radiates light back at different wavelengths. Now, if everything on this periodic table were constant, this wouldn't happen. This is a huge surprise in the world of nanotechnology. The reason it happens is because I've got 10 atoms together, or 100 atoms together, or a few thousand atoms together. And in the world of the atom, they care. They care how many electrons are whizzing around about me and what that electron cloud looks like. And when it's only 10 atoms, it's very different when it's 1,000 atoms. So what actually that means, and this is really rather important, is what was a two-dimensional picture appears now to have some depth to it. There's actually a third dimension, where some of these things that were constant are actually changing. We don't know what they are yet. We don't know how they change, because we're just starting to see things like this. But there are many, many examples like this around the world that we can start to understand. And over time, over the coming decades, scientists who are studying nanotechnology and nanosystems are going to start to understand what this third dimension looks like. Right now, we're just sort of peeking behind and seeing that it's there with experiments such as this. But soon, I believe, we're going to be able to actually make some real predictions about what could happen when I get off into the nano domain. Now, I'll give you a real practical example of what this looks like. And a real practical example is this. Here is, back to my props. Here's a piece of limestone. There's a piece of limestone. Here's the piece I took a picture of. This is from Central Texas. I'm not trying to damage anything here. It's 150 million years old. I just picked it up from a road cut in Central Texas. And it's limestone. There's nothing fancy about it. It's calcium carbonate. It's been around a long time. It's a lot of little animal bodies. That's it. Pretty straightforward. Now, slightly younger is this piece of chalk I picked up at MIT. It's different from this. I could build a building out of this. I wouldn't build a building out of this stuff. I could write on the chalkboard with this. I wouldn't attack the chalkboard with this. It's very different. But no, it's not very different. It's the same stuff. It's calcium carbonate. It's calcium carbonate. What's different is that the atoms are arranged differently. Now, in this case, they're arranged differently on sort of a macro scale. This is not nano technology going on here. It's macro stuff. But I can take calcium carbonate, and I can look at it on a nano scale, and I get something very different again. And that's this beautiful abalone shell with this iridescent mother of pearl on the inside. Guess what? It's calcium carbonate. It's the same stuff as that. It's the same stuff as that. What's different, and this is really what's important here, what's different is that the lowly abalone figured out, and by the way, every abalone's two, when they get together, they give the next generation everything they need to do this. They figured out how to take calcium carbonate and lay it down molecule at a time in layers, so you get this very smooth, iridescent mother of pearl, which isn't just different looking, by the way. It's like 3,000 times harder than this stuff. It's the same stuff, but it's thousands of times harder. Very, very rather important characteristic, physical characteristic, and it's different by orders of magnitude only because of how the molecules are arranged on a nano scale. And this is what nature has learned to do over billions of years. Why? Because the survival of this species depended on it. So now we take a look at where we are today in the business of energy, and, well, I've got coal. Pretty basic stuff. It's carbon. It's basically carbon. There's not much more to it than that. Right? Imagine what the world of energy might look like is if I could take fuel, whether it's something like this or something like this, but do something kind of like the abalone has done in the sense of taking molecules, arranging them differently, and making something totally different, totally new. Something on my clean, cheap, and convenient chart, which actually does hit the sweet spot. Now, is this possible? I think that it is possible. Do I know what it is? No. I haven't the slightest idea what it is. But that's what technology and innovation is all about. But let me give you some examples of how the world gets remade by technology. And maybe that'll kind of bring this around to a close. A few hundred years ago, well, today, let's start today. Today, the most important commodities in the world are the ones I've been talking about, energy. A few hundred years ago, the most important commodity in the world was not oil or coal or natural gas. It was salt. Salt, that's what everybody cared about. That's what nations were built on. That's where many words like salary come from. Right? Roman legionnaires were paid in salt. So salt was the world's most important strategic commodity a few hundred years ago. What? Where'd that go? Well, it went away with refrigeration. Right? So just like that. It didn't matter. And now this is important for thinking about the future of energy. We tend to look at alternative energies as, well, they have to compete. They have to compete with coal. They have to compete. If I'm going to do solar, it has to compete with coal-based electric generation. If I'm going to do oil, if I'm going to do something to replace gasoline, it has to compete with oil. Well, yes, it does at some fundamental level, but I would hazard to say that not on price necessarily. I don't believe that refrigeration was cheaper than salt when it was invented. It certainly wasn't more convenient. It certainly wasn't simpler. But here's the secret. It was better. Right? Not only could I preserve meat without having to pound salt into it, but I could preserve fruits and vegetables and lots of other things as well. So what happened, and why I talk about salt and refrigerators just briefly, is because it's a lesson in technology and in technological revolution. And it says, don't focus just on cost competition, because cost matters. Certainly cost matters, but cost doesn't determine, in my mind, cost doesn't determine the outcome. Utility determines the outcome. And it can be more expensive if it is better. And consumers show this all the time. They always go for better solutions even if they're more expensive. Automobiles were certainly more expensive than horses and more complex and more difficult and required gasoline. But look, they win on utility. And the next energy revolution will know it's here because people will not be talking about, well, does it compete with the price of oil? Can I make electricity for the same as burning coal? No, they won't be talking about that because somehow utility will have trumped that. Now, I'm being honest. I don't know what that looks like other than to say that's what it looks like at a big scale. So I make up what could happen. Well, let me give you an example. And it's from a nano example. Let's say that somebody figures out how to take silicon. Oh, by the way, if I'm talking about energy at a global scale, I'm going to be talking about very common things on this periodic table up here, not the very exotic, expensive, rare stuff as I get deeper into the periodic table. There's an MIT material science professor who very astutely said, if you want to make something as cheap as dirt, you better make it out of dirt. So, and this is important, ultimately. So just imagine if I could take silicon and I could borrow from the abalone, because this is biologic, it's self-assembly. The abalone does this all by itself. People don't have to go in and arrange. Nobody has to arrange the molecules this way for the abalone. It does it all by itself. So what if I actually had a silicon-based paint that borrowed from this self-assembly characteristic, and when I painted it on my house, the silicon atoms linked up with other constituents in the paint to make electrical circuits, and all of a sudden, the whole outside of my house was a solar panel. Now, I'd probably pay more for that than I would regular paint. And, oh, by the way, it's made out of silica, so it's really durable. So I'm winning on utility as well. And it might be a little more expensive than some things, but that's the sort of thing that totally remakes the world of technology, and could certainly remake the world of energy. And so with this, we go back. Sorry, okay, there. This is 1908. This is in Philadelphia. And it's what you see here is everything. There's horses, there's little automobile things, there's trolleys that are possibly electrically driven. There's every sort of mode of personal transport imaginable in this picture in Philadelphia from 1908. And it's all happening. And the important point here is it's now 2012, 100 years on, and you would never, if you were on this street in 1908, you would have never guessed that 100 years later, the dominant form of personal transportation would be the gasoline-powered automobile, and that the buses and trolleys would now be diesel-powered. You just wouldn't have guessed it. Why? Because the engines didn't really exist in great numbers, and the fuels didn't exist, and there wasn't the capacity and the infrastructure, and many, many other reasons. You wouldn't have imagined. And this is really critically important. As we think about the futures, as we think ahead to 2100 and beyond, don't imagine today, while I can muse about, well, I can make something kind of like this in that it's a fuel, but kind of like this and it has all these neat bio self-assembly, kind of like this in that it's liquid and easy to transport. I can ponder all of this all I want, but I can't predict where the answer is. Right? We cannot pick the winners. And this becomes very important from a political sense because politicians, unfortunately, like trying to pick winners. they start with picking themselves as winners, and then it just gets all out of hand. Right? So that's critical. Okay? We cannot imagine today that we know what the answer is going to be, but we have to put in place the structures, social structures, financial, legal, technical, have to be in place so that lots and lots of things can compete, and the winners will emerge. Okay? The best ideas will come to the top. That is really the bottom line, except to say that scale is critically important in all of this. Right? So I don't know, I started talking about a half an hour ago, and I started counting about a half an hour ago. And in the half an hour that I've been up here, the world has gone through some 291 million liters of petroleum. And it continues. This is it. This is the scale of the energy systems that we have in the world. So this is the scale of the challenge that's ahead of us. We have to replace something that operates at that scale, but it's also the scale of the opportunity that's before us for coming up with the new ideas and the new technologies. And that's where I will leave it. Thank you.